In this video, we describe how to apply the first law of thermodynamics to a process at constant volume and engage in a discussion of state functions versus path-dependent variables. All right, so the goal then would be to try to first apply the first law to a process at constant volume. Right, so let's try to do that. This is the first law of thermodynamics, and we want to see what happens when you try to apply this law to a process in which the volume is constant. Okay, so this is going to be a simple a process. The system has to be quite simple. It could be a gas, or it could be a liquid, a solid, perhaps a chemical reaction, something like that. And a key characteristic of this exercise is that we're not making any attempts at harvesting any work from the system other than expansion work. Okay, so there's various types of work. You could have expansion work, which is something that we have seen in earlier videos, but there's also things like magnetic work, or maybe electrical work, or maybe muscular work, like I'm doing, to be able to localize or to hold this thing and so forth. Now those tend to be quite complex, but for simple chemical systems, like again a chemical reaction in a container, or maybe a gas, an ideal gas, or a mixture of gases, then none of those electric or magnetic or muscular work are possible. Only expansion work would be possible. But if we're working under constant volume conditions, right, that's kind of the idea here. So let's try to see what happens here at constant volume. Then the only type of work that you can do is expansion work, but the volume is constant, right? That means that your differential of V is 0, then work is 0. Okay, so then what happens is this: at constant volume, okay, for these simple systems, work is going to be 0, and then what happens is that delta U is equal to Q, and as a matter of fact, we're going to write here Q sub V, and this is important. That means that this is the heat transferred as the energy transferred as heat at constant volume. Okay, and that is an important expression. Okay, again, this is a very simple way to apply the first law, but it's an important one because it tells you that the very important thermodynamic variable that we call the internal energy, that can be obtained if you are able to do the process of constant volume and then measure the energy transfer as heat in that process, right? Again, how simple this is, right? You can calculate the change in internal energy if you're working at constant volume, and then that will be just the energy transfer as heat. If you're able to determine that energy transfer as heat in that process of constant volume, then that will be exactly the same thing as the change in internal energy. So this is very powerful. You can do it because it's very simple, right? Again, you just have to measure an energy transfer as heat, and you're done. That's your change in internal energy. Okay, so again, that's a very powerful expression, and we will see more about this a little bit later on. But this is a good time to talk about something that is a little bit abstract, but also very important, and that is the concept of path-dependent variables and state functions. Okay, so let's first state what those things are, and then try to see if we can explain a little bit more with a deep level of detail what the implications of those definitions. Okay, path-dependent variables are those that depend on how the process is carried out. And we have said that for path-dependent variables, which I'm going to write down here in this column, right, there's two that are key: work and heat. Okay, so it actually matters if you're doing a process at constant volume or at constant pressure. The amount of energy transfer as work and heat will be different. Okay, and again, that's just a characteristic of path-dependent variables. However, the internal energy actually does not depend on the path. It turns out that it really doesn't matter how you do the process. The change in the internal energy, okay, will always be the same regardless of whether you're doing this at constant pressure or at constant volume. What that means is that this internal energy is a state function. And the name state function comes because you can compute changes by just knowing what the final state of that system is and the initial state of that system is. How the process goes, how the system goes from the initial state to the final state is completely irrelevant to the value of the change in that state function. We're going to illustrate these concepts using height, which is also a state function. So let me actually then write here this state function. So the internal energy will be a state function, but then height, which I'm going to write as h, is also a state function. So let's demonstrate that height is a function of the state. I'm going to calculate the difference in height from the initial trace of this marker to the final one. Okay, so the initial trace is this one, and the final one is that one. And again, I'm interested in calculating delta H. Okay? So fine, that's fine. The only thing you have to do is we'll figure out what the height of this initial trace is, what the height of this final trace is, and that difference will be just delta H. Fine. But notice that this delta H actually does not depend on how I move the marker between the initial point and the final point. Right? I can go back to the initial point and then do this. Final point, there you are. Right? Delta H is still the same. Okay. However, the amount of work that my arm has done and the amount of heat, transverse heat, is different in those two processes. As a matter of fact, you could actually do something like this, right? That's still a way, initial point and final point, in which delta H is the same. It's about 3 inches or so, right? But work and heat are not. Okay, so the same thing happens for the internal energy. Okay, it really doesn't matter how you go from the initial point to the final point. The only thing that matters is what is the initial point and the final point. What is the initial state and what is the final state? That's why it's called, the internal energy and height are called state functions. Okay, and again, work and heat are not. They obviously are, they are path-dependent variables. Okay, so here comes the interesting thing. And that is to say that, well, we just wrote an expression which was like this, in which you're relating these two path-dependent variables to a state function, okay? But then what we've done is actually said, well, we're going to specify the path. Okay, we're going to say, well, we're doing this at constant volume, and then if you do this at constant volume, then the idea is that that disappears, and this q turns into q sub v. Now this number right now is no longer a path-dependent function because you are specifying the path. We're actually saying, well, that's not any heat, that is the heat at constant volume, right? So that's no longer I mean, you're specifying the path, and then what that means is that, well, you can equate that now to a state function. Okay, so again, this is a little bit abstract, but these concepts will be very important for us to solve problems in the future, in which we will be able to use this expression, okay, to always calculate delta U. Notice that the key here is going to be that delta U does not depend on how you do the process, right? So if you're able to calculate Q sub V, regardless of how the process is done, right? So suppose that the process is done at constant pressure, right? What will happen is that this heat will be equal to Q sub P if the process is done at constant pressure, but it will not be the same thing as if the process is done at constant volume, right? Working at constant pressure means that this is true, but this is not true. Okay, so even if you're working at constant pressure, what will happen is that if you're able to calculate this Q sub V, right, then you will be still be able to determine delta U, because the internal energy does not depend on the path. Okay, so let me say this once more. What we're explaining in this video is actually intellectually quite challenging. And the only way to really understand this is to actually do a few problems in which we have set up a way to see this much more clearly. I guess that the important thing in this video is to recognize the following. Work and heat depend on the path, the internal energy does not depend on the path. If you're fine with that definition, then with the problems we're going to be working on these concepts of when are things path dependent, when are things not path dependent, when is it that I can use this expression, when is it that I cannot. But again, if you get comfortable with the idea that internal energy is a state function, then your work in trying to solve the problems will actually be very simple, And again, we will see some examples of that as we do the homework.